Hello, my name is Gaynor Payton and I'm the Director of Geosciences with Geoteric. My e-lecture today is about frequency decomposition of seismic data, the techniques and applications. Seismic interpretation is all about understanding the geology that's hidden within the seismic data. And frequency decomposition can help us do this by showing us the geology right at the start of our interpretation. So what I'm going to look at in this presentation is exactly what frequency decomposition is, why we need it, what the different techniques are, and how we can visualize and interpret the results. I'll also be showing some applications of frequency decomposition and RGB blending. So frequency decomposition is a way of viewing discrete elements of the data by looking at band-limited sections of our frequency spectrum. This gives us greater insight into the information that's contained within the data. It's a bit like having a big bowl of soup, which is a mixture of all sorts of ingredients. What you're tasting is the entire thing. If you want to understand exactly what goes into that soup, you need to be able to identify each of the component parts. And that's what we do with frequency decomposition. We take out the individual ingredients, the component parts, so that we can understand them in more detail and look at them individually. So we do this so that we can actually see the geology that's hidden within the seismic data. It shows us a lot of geomorphologies, a lot of channel shapes, carbonate reef features, information about the shapes and sizes of our geology, but it can also provide information on thickness, on lithology, and also on pore fill. For example, if we take a look at this image, what we can see is an envelope volume that's been draped on a horizon, and we can see a zone of high amplitude in red, and we've also got a zone of lower amplitude, which is more of the bluey green colors. So we can see we've got changes in there, but we can't really identify the geology. We can't see clearly what is going on. However, if we run frequency decomposition on this and create an RGB blend of 3 of the frequency responses, the geology suddenly becomes a lot more apparent. Now we can see clearly that we've got 2 channels cutting across this horizon. We can see the edges very clearly, and we can also start to see internal heterogeneity. So we can see the thalweg coming through, we can see lateral accretion parts, we can see point bars as well. So by looking at frequency decomposition and looking at a blend of multiple magnitude volumes, we can get more insight into the geology that's in our data. It's important to understand the different methods of frequency decomposition because they all have their advantages and also their disadvantages. There's always a trade-off between frequency resolution and vertical resolution, and this is governed by the uncertainty principle. There are many types of frequency decomposition, but the 3 that are used most commonly with seismic data are a Fourier transform, continuous wavelet transform, and matching pursuit. And these are the 3 techniques that I'll be looking at today. So it's important to use the right technique for your interpretation objectives. So using something like a Fourier transform or a continuous wavelet transform is very good if you're doing regional studies, reconnaissance, where you're looking at large areas and you want to understand the geology and understand what's going on in those areas. It's also very good for identification of gross geological features and for estimation of bed thickness because you've got very good frequency resolution. On the other hand, something like a matching pursuit-based technique where you've got good vertical resolution is very good if you're doing reservoir analysis, if you're looking to identify subtle depositional changes, and if you want accurate vertical localization in your results. This can be seen in this next slide, where we look at the different types of frequency decomposition and the effect that they have on both the frequency resolution and the vertical resolution. So on the left-hand side, we have our original frequency spectrum and an inline showing the envelope response, so the magnitude of the response. On the left, it's the full frequency, so we're seeing all the frequency components, and we've got very good layering coming through. We can see where we've got the high amplitudes in yellows and reds, and the low amplitudes in blue. If we run a frequency decomposition on this using a Fourier transform centered around 20 Hz, we get the 20 Hz response, and we can see in the graph that it's a very localized response. So we're looking at a narrow bandwidth of data. It's only taking part of that frequency spectrum. But because of this, it's got very poor vertical resolution, and you can see in the data that there's a lot of smearing vertically, so we can't see the discrete layers very clearly anymore. It's hard to define exactly where the top and the base of those high amplitude layers are. If we look at the continuous wavelet transform, again centered on 20 Hz, we see we've got a slightly wider bandwidth, so we've got slightly less frequency resolution, and this has given us an improved vertical resolution, so the responses are slightly more localized. And if we take this on further into the matching pursuit, again centered on 20 Hz, we've got a much wider bandwidth now, and that gives us much better vertical resolution. So the layers are more distinct again. We can see clearly where the top and the base of each event is, but our bandwidth is much wider. So we're looking at more of the frequency spectrum, and there's less frequency resolution. So depending on whether frequency resolution is important or vertical localization is important, then you use the appropriate technique for your interpretation objectives. So when we do frequency decomposition, we usually decompose it into multiple bands, not just one, and we can look at the differences between the different frequency bands, and this will start to reveal different parts of the information. So what we have here are 3 frequency responses at 30 Hz, 40 Hz and 50 Hz, and we can see that there are subtle differences between them. These are all coming out of the same input data, but they're just looking at different parts of the frequency spectrum. So at the moment, if we view them individually, we have to compare them to look at how the images are changing and then make inferences from that, which can be quite a time-consuming process. So it's much easier if we combine them together into one volume, and we do this using RGB blends. So the 30 Hz response goes into the red channel, the 40 Hz response into the green channel, and the 50 Hz response into the blue channel. And when we do this, we get a blend that shows us the contribution from all 3 volumes. So where we've got areas of white, we've got a strong high amplitude response in all 3 volumes. Where we've got black, we've got low amplitude response in all 3 volumes. And where one color is dominating, then that frequency is dominating. So what we can see here quite clearly is the geometries of the 3 channels and the 4th cross-cutting channel. They're coming out really nicely, as well as the internal heterogeneities in them. But we can also see in the backgrounds, particularly on the right-hand side, that the background color trend is changing from blue up in the north to a more brownish red down towards the south. This means that down in the southern area, we've got a greater contribution from our lower frequencies. So this could be indicating a thickening up of our sequences and of our reflectors as we go down to the south. So if we zoom in on the top of those channels again, we can see the different faces that we saw earlier that are being highlighted by the different frequency characteristics. The different colors are showing up those different faces. So we can see the Thalweg is more of a blue color, the point bars are more reddy brown color. What we can also see on the left-hand side with the channel on the left is that the colors are more variable. There's more changes within that channel, and that indicates heterogeneity within there. Maybe changes in thickness, or it could be changes in the lithology in that channel system. But it's important that we don't just look at the RGB blends and leave it there. There are tools available that allow us to interpret directly on the RGB blend, to extract out adaptive geobodies that show us the morphology, so we can get a 3D interpreted object of those channel features. From that we can get volumetrics. We can also do facies classifications directly on the RGB blend, so we can start to interrogate the geophysics a bit more, look at the variability of the classes, the variability of the frequency response, and start pulling out the individual facies based on the seismic response. So frequency decomposition and RGB blending are applicable at all stages of the interpretation cycle, through exploration, appraisal, into development and production. Now I'm going to show you a couple of case studies which show some of the ways in which you can use frequency to aid your understanding and aid your interpretation. So the first is looking at geological reconnaissance. So if you've got a new area that you're looking at, you've got a large data set and you want to know what's going on in there, frequency decomposition and RGB blending is a really good way of revealing the geology, of showing you what's going on. So we have an RGB cube here, and we're looking at a time slice just through the middle of the cube. This is about 1,000 square kilometers, and I'm just going to show you some of the features that we can see in this one data set. So on the bottom right hand side here, we've got another complex channel system, and again, quite easily we can see the meander loops, we can see areas of lateral accretion, we can see splays coming in, and we can also see scalloped edges towards the bottom, indicating slumping that we've got coming down in those zones. If we move to the center of the image, you can see that we've got some very strong faults coming through, some large faults, and also pull apart zones. We've got where we've got the abrupt change in frequency response, that's where you've got the big throw across the fault. Where we can see the layering coming down between the faults, that's where we've got the relay ramps coming down, heading from north to south. And we can see down towards the bottom of the image, we've got the horsetail faulting coming through associated with those main pull-apart faults. And then further on the left-hand side, we can see these zones of low amplitude chaotic response, and these are volcanic diapirs, and we can start to see the shape and extent of them. We can see where these two diapirs are getting quite close together and may connect at other layers in the volume. We can also see radial faults that are coming out from this uplift. So the next example I'd like to show you is how we can use frequency decomposition when we're looking at stacked channels to look at the exact depositional layering of these systems. Quite often we'll have overlying channel systems, and we need to identify exactly where one channel is and where the other one starts below it. So what we have here, the RGB blends from two different techniques, so the Fourier transform on the left and the matching pursuit technique on the right. What we can see in the Fourier transform on the left is this nice green channel coming through from sort of north to southeast. But when we look at the matching pursuit response, we don't see it there. It doesn't seem to be picking it up. And this begs the question, why can't we see it? Well, if we shift the horizon up by 30 milliseconds and look at the interval just above it, then that channel now appears in the matching pursuit response. And this is because we're seeing it in its true depositional position. With the matching pursuit, we've got very good vertical resolution, and we're seeing that that channel is existing 30 milliseconds above the horizon. When you shift the horizon down to its true position, the channel is no longer there. The Fourier transform technique is smearing it vertically, so we're getting an image of that channel over a much greater time window than it truly exists. And this can be seen when we look at the vertical section through the two blends. The horizon on the vertical section is at that shifted point, so 30 milliseconds above its true position. And we can see the vertical smearing that we've got on the left-hand side, whereas in the matching pursuit one, we've got distinct layers and we can see much better vertical localization. And that's our channel system there inside the circle, very, very tightly constrained. So the third example that I'd like to show you is how we can use frequency to estimate thickness. And this is where a technique like a Fourier transform really helps, because you get very good frequency resolution. So if we look at a simple wedge model, we can see the difference in the RGB blend of the Fourier transform, the continuous wavelet transform, and the matching pursuit. With Fourier transform, we get a nice rainbow of colors on the different thicknesses of the wedge, and this is due to the destructive and constructive interference that you get between the different frequencies. With the matching pursuit-based technique, you get very distinct top and base surfaces of that wedge, and those are defined all the way right up to the tuning point on the right-hand side. And that gives us the good vertical resolution, but it means that we can't really use matching pursuit very well for estimating thickness, whereas the Fourier transform result gives us this range of colors so we can start to look at thickness. This is illustrated here, where we've got an RGB blend of a submarine fan system on the right-hand side, and we've got a wedge model with a decomposition that matches the one that we ran on the seismic. What we can see here is that our well location, where we know the sand is 84 milliseconds thick, we can use that to calibrate our wedge, and we can look and compare the colors that we're getting in the seismic with what we're seeing on the wedge. And once we've got our wedge calibrated and we know that that color represents 84 milliseconds, we can start to look at other areas of that fan and read off their thickness. So we can see that the thickest part of the channel, which is coming in this blue color, is giving us a response of 110 milliseconds according to our wedge model. So using a Fourier transform technique or a continuous wavelet transform technique, we can start to estimate bed thicknesses from our seismic data. And finally, I want to look at reservoir compartmentalization and how these techniques can be used to look at lateral variability within your reservoir. This is very good in development situations when you're trying to produce from your reservoir and you want to understand any kind of baffles that you may have or any factors affecting fluid flow. So what we have here is the Stybarrow Reservoir from the northwest shelf of Australia, and we can see on the left-hand side an envelope volume where you can see this nice high amplitude response that corresponds to our reservoir. If we look at the RGB blend of the same reservoir, we can see a lot more detail and a lot more color variations coming through across the reservoir. So we can see very clearly that we've got a cross-cutting channel coming along here in blue. We can also see faults that are clearly visible, not only the dark north-south faults, but also the very subtle east-west fault down on the left-hand side near the tip of the reservoir. We can also see lateral variations in colour, so areas of more pinker colours, areas more oranges, areas that are more greens, and these are showing us lateral variations in the frequency response, and that could be changes in thickness of the reservoir, or it could be changes in the pore fill or the lithology. So frequency decomposition and RGB blending can reveal a lot more geology than just looking at a single amplitude volume on its own. It allows us to see the geomorphologies as well as seeing detailed facies information. It's very effective at reconnaissance for identifying stacked channel systems, but also for estimating bed thickness, identifying compartmentalization. But it is very important that you use the right technique for your interpretation objectives, depending on whether you're looking for frequency resolution or vertical resolution. And finally, it's important not to just look at the blends, but to actually use them as the basis for your interpretation. So to interpret directly on the blends once you have your geology revealed to you. And you can then take that on for further analysis into the geophysics and looking at the detailed changes that you're getting within the features that you've identified. So thank you very much indeed for your attention and for listening to this e-lecture. You can share this lecture below or add comments that you may have. And please look at the Learning Geosciences website for other e-lectures and the YouTube channel. Thank you.
Thank you very much.